Next, we're going to look at different ways that we can represent an explanatory variable in a logistic regression model. The reason why we want to examine these different ways is because it will allow us to get a better fit for our model. In other words, we'll be able to better estimate our probability of success, and also we'll be able to better understand the effect that an explanatory variable has on our response variable. Now, for many of you, you have seen these kinds of different ways to represent these explanatory variables in the model. But I expect that there are some readers, some students in my course who have not. So we're going to start with some of the basics here first. The first different way to represent these explanatory variables in our model is through what's called an interaction term. So to relate this to a normal linear regression setting, suppose we have the following regression model. Expected value of y is equal to beta 0 plus beta 1 times x1 plus beta 2 times x2 plus beta 3 times x1 times x2. This part right here is referred to as an interaction term. What it allows one to do is that instead of just using, let's say, beta 1 or let me back up. What it allows us to do is that instead of interpreting the effect that x1 has on the expected value of y by only focusing on beta 1, it allows that effect to change depending upon the level of the second variable. This can be very important in some situations because the way that one variable affects the response can be now dependent upon what is the level of this second variable. Thus, that's why we have this interaction term. Now, in logistic regression, we can also have a model that has an interaction term in it. In fact, we will see an example very shortly where it makes sense to actually include an interaction term in our place-kicking data model that we have. So let's take a look at what a model would look like, just in general. So I have two explanatory variables, x1 and x2. Here's my interaction term right there. So what that says is that the effect that x1 has on the logit of pi is dependent upon the level of x2. Similarly, the effect that x2 has on the logit of pi is dependent upon whatever the level is for x1. Okay. Now, we can use odds ratios then to better understand this effect. Because of the interaction term, the odds ratio will not be the same as what we've seen before without the interaction term. So let's take a look at an example where we have an odds ratio for x2. Now, here's my odds ratio. Again, all that an odds ratio is the ratio of the odds of success at, let's say, x2 plus c divided by the odds of success at just x2 itself. And so based upon my model, I write out my model, or I write out the odds in the numerator and in the denominator. We again have some stuff cancel out in the numerator and denominator. So let me just cancel these guys out here. And look what we're left with. The exponential function evaluated at c times beta 2. If we didn't have an interaction term, that would be it. But now we also have this part right here, c times beta 3 times x1. And so what we can see is that if I want to understand the effect that x2 has on the odds of a success, not only do I look at c times beta 2, but now I also have to take into account whatever numerical value x1 is as well. Thus, the effect that x2 has on the response is dependent upon the level of dependent upon the level of x1. We can then factor that c out a little bit there so that let's say my final odds ratio is the exponential function value at c times the quantity beta 2 plus beta 3 times x1. So how would I now interpret this odds ratio? Well, I could say that the odds of success are the odds ratio, OR times as large for a C unit increase in X2. This is exactly what we would have had before. But now when X1 is fixed at a level of whatever you specify. If X1 was 1, that's going to be different if X1 was -1. Or if X2 was, or let's say if X1 was 100. That's why we need to include whatever value you're holding, let's say, X1 constant at. And in fact, what you may need to do to fully understand the effect that X2 has on the response is try a few different values of X1 and have separate interpretations for each of them. You'll see that in an example coming up. Now, compared to what we had before for that interpretation, basically what we did was, meaning before when we did not have an interaction term, but we did have X1 and X2 in the model, we replace essentially when holding X1 constant, we replace that with when X1 is fixed at a particular value. That's the difference. Now let's say we did have a model that also had an additional term to it. Let's say it was, let me actually come up here to the model. Suppose we also had, let's say, beta 4 times X3 in the model, where X3 is not part of any interaction. If I want to interpret then the odds ratio associated with X2, I would have exactly the same thing, but I would then need to add when holding X3 constant. Okay, now to do inferences corresponding to an odds ratio, we once again can use walled confidence intervals, profile likelihood ratio intervals as well. Let's briefly take a look at a walled interval here. Once again, let's assume that we have this model with X1, X2, and the corresponding interaction. The odds ratio, again, was EXP of C times the quantity beta 2 plus beta 3 times X1. Again, this is for the odds ratio for X2. The walled interval then is that we first find an interval for the C times the quantity beta 2 plus beta 3 times X1. We find that walled interval, so we take that estimate plus or minus the value from the standard normal distribution. That C gets factored out of the variance. We have then the estimated variance of beta 2 plus beta hat 2 plus beta hat 3 times X1. Then to put it back on the odds ratio scale, we apply the exponential function with it once again. How do I find that estimated variance? Well, in very much the same way as what we've seen before, like for example, when we were finding a confidence interval for pi itself, we need to write out the different terms of the estimated variance, where I would have variance of beta, the estimated variance of beta hat 2 plus X1 squared times the variance of the estimated variance of beta hat 3 plus 2 times X1 plus the estimated covariance for beta hat 2 and beta hat 3. Where do I get these individual variances and covariances from? Estimated covariance matrix. And so once again, this result here is applying this expression that we've seen before. Okay. Now, generally speaking, profile likelihood ratio intervals would be preferred, and they're calculated in much the same way, where we're trying to find the set of particular values that satisfy -2 log lambda is less than the corresponding quantile from a chi-square distribution. Unfortunately, some of the computations can be more difficult to make. We will use the MC profile package for this purpose. Okay, a few general comments here before we get to an example. Now, the individual explanatory variables that you see represented in the model, like X1 and X2, they are often referred to as main effects, where the term X1 times X2 is referred to as an interaction. So just some terminology. How can we then represent this particular model, where we have X1 and X2 with its interaction, how do we represent that in the correct R syntax when we use the GLM function to estimate it? Well, in the formula argument, there are actually 3 different ways to represent it. The first way, we write out x1 plus x2 plus the way to do the interaction is to put a colon between x1 and x2. Now, there are, let's say, somewhat simplified ways to represent this model. If I did x1 asterisk x2, what R recognizes this as is that you want the main effects and the corresponding interaction. And then lastly, one could put in parentheses x1 plus x2 and then caret sign 2. This doesn't mean that I add x1 to x2 and then square it. Rather, this caret sign says, okay, I want basically, I want all 2 ways interactions to be represented in this model in addition to the main effects. So one could actually have something like this as well to help explain this. Suppose I have 3 variables now, x1, x2, and x3, and I put a caret sign 3 there. What that's going to do is have x1, x2, x3 in the model, plus all their pairwise interactions. And sorry, it takes a while to write all this out. And then also then the 3-way interaction as well. Generally speaking, in this class, except for, or in this in my course, I typically don't look at too many cases where you have 3-way interactions, 4-way interactions, and stuff like that. So unless otherwise I tell you, we'll just stick at the 2-way interactions. Now, there is a particular convention that people use when including interactions in the model. So if I have an x1 and x2 interaction, I need to also have the corresponding main effects. If I had an x1, x2, and x3 interaction, I need to have the corresponding 2-way interactions and the main effects as well. This convention is often referred to as the principle of marginality. If we didn't do that, then you can get some, you can say, odd shapes to your model, and the model might not work out as well as you would like. So that's why we use this convention. This is very common throughout all of statistics. Okay, let's now take a look at an example. So we're going to go back to the place-kicking data set once again. And what one would, if you're a football fan, what one would expect is that the longer the distance of the place kick, the more of an effect that wind can have on it. Because wind will have a longer period of time, because it takes a while for the ball to travel in the air, wind will have a longer period of time where it could move the ball in the air, depending upon the wind speed and the wind direction, stuff like that. So the effect that wind has on the probability of success is dependent upon what the distance is. That's what most football fans would think. And what I'm just describing to you right now is an interaction. The effect that one explanatory variable has on the response is dependent upon the level of another explanatory variable. So let's take a look at a model, logistic regression model, that includes distance, wind, and the distance and wind interaction. Okay. Now, just to review, the wind explanatory variable has just 2 levels to it. One for windy conditions, a 0 for non-windy conditions, or attempted inside of a dome stadium. So we have just 2 levels for it. Here's how I can represent these explanatory variables and the interaction in my model. I'm going to put the results into mod.fit.ha. We're going to end up doing some hypothesis testing later where this will be the alternative hypothesis model. So that's why I'm using that as my object name. And then I'm going to say GLM, my response variable good, tilde. Put in my first explanatory variable, the second explanatory variable, and I'm going to put in the interaction like this: distance, wind. Everything else remains the same as what we had before. I can use the summary function to summarize then the corresponding results. So if I want to state then my estimated logistic regression model, I'm going to look at the estimate column, and I could say that the logit of pi hat is equal to 5.684 minus 0.11 times distance plus 2.47 times wind minus 0.0837 times distance times wind. So look at my interaction term right here. Now, one of the first things that you might want to do then is to do a hypothesis test of, is beta 3 equal to 0 or not? Beta 3 would be the corresponding regression parameter for the distance and wind interaction if I were to write out then the corresponding population version of my logistic regression model. And so what one could do to get a wall test is that one could come back up to our z-value table. I see a value of negative 1.9 there. The corresponding p-value, then using a standard normal distribution approximation, is 0.0531. So because of that, then there is marginal evidence that the distance and wind interaction is important. How about a likelihood ratio test? Well, I can use the little ANOVA function. I can use the capital ANOVA function. In this particular case, I'm going to use the little ANOVA function first. So to do that, I'm going to take this approach where I need to first estimate the model without the distance and wind interaction in it. So this could be, let's say, my null hypothesis model. Then in my ANOVA function, I put my null hypothesis model, I put my alternative hypothesis model, and to say that I want a likelihood ratio test, I say test equal chi-sq. Here are the results. My negative 2 log lambda statistic is 5.1. My corresponding p-value is 0.02379. In other words, the probability that A, where A is a chi-square 1 random variable, is greater than 5.1 is 0.02. So once again, I have marginal evidence that the distance and wind interaction is important. Let's take a look at some notes corresponding to what we've just been doing. So if we come up here to the model itself, notice how I have a negative coefficient on distance. My estimated value for beta 1, or in other words, beta hat 1, is a negative 0.11. And if we see what happens when wind is equal to 0, we see that we have a negative effect in terms of as the distance increases, the probability of success will goes down. But then also take a look at this. I have a negative coefficient on the distance and wind interaction. What that says is that the amount that this probability of success goes down as distance increases actually causes the probability of success to go down more quickly, you could say, because I have a negative coefficient on there. Now, we do need to, though, take into account the fact that I do have a positive value for wind. But if you look at the longer distance values, such as 50 yards, 60 yards, that positive there doesn't counteract the fact that I have a negative there in terms of my probability of success will be farther down than what it would have been if wind was 0. We'll take a look at a plot that explains that even further shortly. Okay. Now, another way that we could have done our likelihood ratio test is to use the capital ANOVA function as well. And so if I do that, and it's maybe a little bit easier because I don't have to estimate separately the null hypothesis model, we see that we get the same test statistic and the same p-value as before. But one reason why I want to bring this up is that I wanted you to take a look at this part right here. We have some -2 log lambda statistics and corresponding p-values, but you have to be very careful interpreting those particular values. The reason being is because the capital ANOVA function uses what's often referred to as a type 2 test format. This is a format that you might have heard of if you've taken an experimental design class before. And basically what this basically says is this. You can think of the distance and wind interaction as a higher order term in the model because it's more complicated. And so using a type 2 test format, what happens is that it will perform the tests in this particular case for the main effects without considering the interaction. Why? Well, remember that principle of marginality before. If you can only have an interaction term in the model if you have the corresponding main effects too. So because of that, type 2 tests say, okay, for my wind row of the capital ANOVA output, I'm going to do this hypothesis test where we don't have that interaction at all. For the distance row of the capital ANOVA output, it does this particular test, but it assumes that there's no interaction and that wind is always in the null and alternative hypothesis models. So let's take a look at a plot of our model. So if I were to estimate a model without any interaction term at all, this plot on the left is what I would get. And so that we can see that under windy conditions, meaning that when wind is equal to 1, the estimated probability of success decreases, as one would expect if you're a football fan. So that decrease is measured by, you can see the differences between these lines throughout for all the distances. But now with an interaction in our model, look what happens. Remember how we had those negative coefficients on our model. And we can see that for the longer distances, there is a much bigger effect for having windy conditions than for not windy conditions. This matches what our idea of interaction would be, that the effect that wind has on the response is dependent upon the distance itself. Now you might be warning, well, wait a second, Chris, take a look at this. Under windy conditions for shorter place kicks, you have a higher probability of success. Well, in this sample that occurred, but I will tell you, first of all, wait a few minutes and I'll explain that further. So let's take a look at odds ratios to help us better interpret the effect that wind has on the odds of a success. So I'm going to compare windy versus non-windy conditions, holding the distance constant. Here's our corresponding odds ratio. This is exactly what I showed you before, where x1 is distance, x2 is wind. Notice you do not see an x2 in there at all. You don't see that wind. But what is dependent upon is the value of c, and for us it has to be c equal 1, because wind can only be 0 or 1, and we do have a distance in there. So since distance is in there, you need to decide when you do this interpretation, well, what distances should I use? And there isn't necessarily always one right choice. I decided to choose distances 20 to 60 by 10 yards. Again, 10 yards has a special meaning in football, so that's why I chose 10. So let's take a look at how we can find the estimated odds ratios, the corresponding walled confidence intervals as well, using R. Now do note that this is, you could say, the longer way to do this. I will show a shorter way later, but it is good for you to understand this longer way too. So that's why we're going to do this. Okay, so the first thing I'm going to do is I'm going to create a vector called beta.hat. that contains beta hat 1, beta hat 2, and beta hat 3 in it. So here we go. So that if I were to say beta dot hat left bracket 1 end bracket, I get beta hat 1. Now note that mod.fit $sign coefficients. Can't type today. Oops. Wrong model. There we go. Note that that has a length, that is a vector of length of 4. And if I were to ask for the very first element, I don't get beta hat 1, I get beta hat 0. So to help correspond what I put in brackets to what we actually represent the beta hats to be in terms of the numerical index, that's why I decided to create beta hat here. I'm going to let a value of C be 1. I'm going to create some distances of interest. So I'm going to use the seq function for sequence, a sequence from 20 to 60 by 10. And then I'm going to find then the corresponding estimated odds ratio for wind. What do I use? I just basically program in the corresponding equation that we just saw. Beta hat 2 plus beta hat 3 times distance. I multiply it by C, which is just 1 here. Did I need to put C? No, but I did this in case you want to take this code to other problems where you wouldn't have a binary explanatory variable. So if I go ahead and do that, and let's take a look at or.win, there's my corresponding estimated odds ratio. So for example, the estimated odds of a success are 0.08 times as large for windy versus not windy place kicks at a distance of 60 yards. Next, what I'm going to do, something similar to what I did for beta hat, I'm going to pull out of the estimated covariance matrix the rows that I need corresponding to beta hat 1, beta hat 2, and beta hat 3. So for example, this element here in my estimated covariance matrix is the estimated variance of beta hat 1. Then I can program in the corresponding equation that I need for that estimated variance, where I take out the corresponding elements of the estimated covariance matrix as needed. Next, I find my confidence interval for beta hat 2 plus beta hat 3 times the distance, and I multiply it all by C. Sorry, I should have said I'm finding the confidence interval for C times the quantity beta 2 plus beta 3 times the distance. So let me go ahead and do that. So here are my lower bounds. Now, remember what distance is. It has 5 elements to it, and R correctly does the math like what we want it to so that we produce 5 different lower limits. I can put all these results then into a nice data frame. I can round the various values, and here's the corresponding results. Okay, so this table here represents, I want to compare windy conditions to not windy conditions. So windy in the numerator, non-windy in the denominator for my odds ratio. Because I often like to have odds ratios that are greater than 1. So if you notice here, a lot of these are, or I guess 3 of them, or actually 4 estimated ones, are below 1. I'm going to actually invert then the corresponding odds ratio. And so I just create a new data frame for that where I do take 1 over the corresponding results. And this is what I get. Let me actually go on over here to Word. So this, we'll take a look at 5.57, distance of 50 yards. So the estimated odds of a success for a place kick are 5.57 times as large for non-windy than windy place kicks. So again, I inverted the odds ratio there. The corresponding confidence interval is 1.54 to 20. Notice the value of 1 is not inside that confidence interval. So what this says is that there is sufficient evidence to indicate that the probability of success is affected by the wind for these longer place kicks, these 50-yard place kicks here. Notice 1 is not in the interval for distance of 40 or for 60 as well. However, for distances of 20 and 30, the confidence interval does contain 1. Let's go back to our plot. Remember how I said, well, we don't need to worry about these shorter place kicks in terms of how the estimated probability of success is larger for windy than non-windy. The reason being is because when we did the corresponding confidence intervals to interpret what happens at 20, what happens at 30, so that we can make generalization to the population of all place kicks, we see that 1 is inside that confidence interval for the odds ratio, so therefore we do not have sufficient evidence to indicate that for the population that the probability of success or the odds of success are affected by windy conditions. But we also hopefully can draw some intuitive understanding here. We see how big some of these differences are here for these larger place kicks. And at those larger distances, we have those odds ratios, the confidence intervals for the odds ratios, not having 1 in them. Okay. Let's get back to where we were. Okay, I think I've talked about all those notes. Here's then, you can see this on your own, the corresponding interpretation relative to the confidence level, confidence interval itself. Notice how you have to specify again which distance you're talking about. Okay, let's talk about a little bit of an easier way to do these confidence intervals. This involves the EM means package. To some respect, this does make it easier, but in other respects, you see the little quirks of the package to do these calculations. Once you understand the quirks, then this is an easier way to do this by far. But the problem is getting used to these quirks. Okay, let me go back to my program here. So, similar to what we've done before with the EM means package, I'm going to create an object called calc.s, means calculate estimates. And it's going to get the results from the function EM means. And the model fit is in mod.fit.ha. Now for my specs argument, I specify I'm going to do these calculations with respect to distance and also wind. Notice I do not need to put then the corresponding interaction. This is what makes this different from a formula argument for the GLM function. All this does is specifies your variables of interest. Now, I want to do some calculations at particular distances. So with inside here, I'm going to create my list, and I'm going to say distances 20 all the way up to 60 by 10. I want some estimated probability of successes first of all. And so that's why I had type equal response there. And so if I type calc.s, we can see what's in there. Notice it calculates the estimated probability of successes for 20 to 60 by 10, but also includes wind equals 0 or 1. If I wanted to, I could also said wind equals C 0, 1 and get exactly the same thing. But I don't need to do that because by default, EM means we'll look at all your different levels of your explanatory variables and do the calculations for all those levels. And so that's why I didn't need to do that. Since there was only 2 levels, it automatically found that. So here's the corresponding estimated probability of successes. We also have confidence intervals for pi as well. We don't want that though. Also, let me just mention that there is a summary function as well with calc.est, and you get exactly the same results here. A little quirk that maybe is not too important for readers or students in my course. an odd quirk of this particular package is that when I just type calc.s here, normally what R would do, it would look for a particular function in the package called print. And then that print function would then print some results, depending upon whatever the author of the package would be interested in. But instead of having a print function, when I just type calc.s there, the authors of this package have it set up so that it automatically goes to summary. So to some respect, it's convenient, but it also doesn't match the coding conventions of R that are normally followed. Anyway, just a small side note. Okay, now I want to get my odds ratios, and I have to do an intermediate step first, where I use a function called contrast. Now, I would expect that all of you have seen or heard the term contrast before. It's frequently used in introductory stat course when you do a ANOVA, and this is kind of like a contrast in that setting. If you haven't heard of a contrast before, that's okay. Basically, what a contrast allows you to do is take a linear combination of some items, like parameters. So if I say contrast object equal, I use the results that I calculated from EM means, and then I want some pairwise comparisons. This will allow me to compare windy versus not windy. Excuse me. As you will see shortly, it actually does the reverse, non-windy to windy, and I'll explain why coming up. And then simple here says, well, what do I want to compare? I want to compare wind, and you have to, unfortunately, include this in a list like this. Combine equal true. For now, just think of it as a way to nicely display the results. I'll explain more what it does as well coming up. So I put the results into an object called test.info. The reason why I use that information, or use that object name, is because actually it provides some hypothesis tests for an odds ratio. Is the odds ratio equal to 1 or not? Actually a wall test, which is something that I generally don't ever talk about in a course because I'd rather have a confidence interval for it. And so what you see here at a distance of 20 yards, it's doing an odds ratio of not windy versus windy. And the reason why it chose that ordering versus the other ordering of windy versus not windy is because the way that we make this coding here of 0 for not windy, 1 for windy, 0 comes before 1. Simply put, that's why it chose that. Here's the corresponding odds ratios. We've actually seen those estimated odds ratios before. It does a Wald's test statistic, and it does some p-values here. Don't look at those p-values. Those p-values actually have a correction associated with them to control the family-wise confidence level, something which we will also discuss about more later on. Okay, then next, I use confident to find confidence intervals, where I have to take the results from test.info to do this. I cannot go all the way up here to calc.s and use that instead. That's a quirk. I want 95% confidence intervals, and I do not want to control the family-wise confidence level at all. I just want strictly 95% walled intervals for each distance. And let's go ahead and do this. Here's my corresponding confidence intervals, the estimated odds ratios, and you'll note that these match what we had previously in the notes when we were doing all of these calculations, programming them in, you could say essentially by scratch. Okay. Now, this adjust argument here. This allows me to do family-wise, to control the family-wise confidence level. One of the most common ways that people to do that is use what's called a Bonferroni adjustment. This again is typically taught in an intro stat course, so I won't go into too much of the details behind it. But basically what happens is that the overall family confidence level that each of the intervals work, meaning that they contain the true odds ratios, is at least 95% in this particular case. I guess I will give you a little bit more of an explanation. So instead of, let's say, using, let's say, instead of using the 1 minus alpha quantile from the standard normal distribution when it finds the interval, instead it uses the 1 minus alpha divided by g, where the alpha is divided by g, not the 1 minus part. 1 minus alpha divided by g quantile from the standard normal distribution, where g is the number of, let's say, comparisons or calculations that you're making in terms of, in this particular case, I have 5 different odds ratios. So G would be 5. So that's what's happening there. Okay, let's take a look at some notes here. Let's make sure that I talked about all this. Hold on a second here. Now, there might be times where you, let's say, want to compare, rather than having the level of 0 in the numerator and 1 in the denominator for that corresponding odds ratio, you might want to reverse that, so that you, in our case, would be windy in the numerator, non-windy in the denominator. How would you do that? You can add in the contrast function reverse equal true to do that. Well, what about, let's say, if you want to do a comparison now for the distance odds ratio. So I shouldn't say comparison, but you want to find the corresponding odds ratio for distance. Well, you would need to hold wind constant at either a value of 0 or 1. You can go through the details on your own here. Here's the corresponding odds ratio, what it would be, where x1 is distance, x2 is wind. We can then also use the EM means package to quickly find this stuff. Notice the differences here. For my at argument, I specify I want the distances of 20 and 30. Let's actually go back here. Sorry. Now notice here, this C would be the increase in the distance. So, we've been looking at often a 10-yard difference in these distances. That's, again, what C would represent. Now, unfortunately, there isn't a way in EM means to say, hey, I want to use a C unit increase in my explanatory variable. And so, again, a quirk of this package is that we kind of have to use like almost a little trick to do it. And so if I want C equal negative 10, notice what I do here. I choose 20 and 30. So if I take 20 minus 30, I get negative 10. I could have chose 40 and 50. I could have chose 35 and 45. The key is the difference has to be negative 10. Then, in terms of other changes, here's my confident function. And what you will often see people do when they use the EM means package and they want confidence intervals, they will embed that contrast function part inside of confident itself. The authors could have made this a lot easier if they would have just simply allowed one to put the calc.s part into confident, but unfortunately they did not. So one will often embed then contrast that use of that function inside of confident, where now object equals the results immediately found from that contrast function. Notice inside of contrast, instead of having list quote wind end quote in parentheses, now I do it for distance for the simple argument. And so here are the corresponding odds ratios. Notice how these odds ratios do not contain 1. So so you can see some of this on your own as well. Here are the standard interpretations that we would have in this particular setting. I guess we can take a look at one. With 95% confidence, the odds of success are between 2.5 and 3.56 times as large for a 10-yard decrease in the distance under non-windy conditions, meaning that wind is equal to 0 here. So there's the corresponding odds ratio. Now, one thing that you also will have to be careful about is that the way that EM-means is set up is that, notice basically what happened is that R ran out of space. It didn't have space for the lower limit here. It didn't have space for the upper limit here. So I had to go down to the next rows. But unfortunately, it doesn't include the corresponding labels then for those rows. So you have to be careful and match it up. In this case, we only have 2 odds ratios, so it's not a big deal, but we'll see other cases where we have a lot more odds ratios and it does become a big deal. Okay. Now, how can we do some of these profile likelihood ratio interval calculations? We're going to focus just on the wind odds ratio here in the notes. And so to do these calculations, I need to calculate, I want to calculate an odds ratio for wind corresponding to a distance of 20 yards, 30 yards, all the way up to 60 yards again. And so what that means then for us is I need to create a correct K-matrix to get the necessary calculations. Okay, so here's my odds ratio once again that we've seen before, where x1 is distance, x2 is wind. Let's first take a look at what the resulting K-matrix looks like, and then we'll talk about how we can actually form it in R. So here's the K-matrix. The first row of the matrix, I'm going to set it up so it's my wind odds ratio with a distance of 20 yards. So notice in this expression here, I have a coefficient of 0 on beta 0. I have a coefficient of 0 on beta 1. And then I have a coefficient of, remember that C is equal to 1. I have a coefficient of 1 on beta 2, so that's why you see that there. I have a coefficient of, well, whatever the value of x1 is on beta 3. Well, x1 is going to be 20 to begin with. And then you can see, all the way down to a distance of 60, we have something similar. So how did I create this matrix? Okay. So I use the matrix function, and I say data equal, and then I nicely try to enter stuff in by row, even though I don't have to, just good coding practice. I try to enter in the particular items in my matrix by row in terms of how I would expect to see them. And so here's that first row that we looked at. Here's the corresponding last row. I have a total of 5 rows I'm interested in because 5 different odds ratios. The number of columns is 4. Beta 0, beta 1, beta 2, beta 3. Okay. Next, I need to use an argument called by row. What that tells R when I say true with it is that I want R to enter in these values that you see here by row. Now you might expect, well, shouldn't that always happen? Because look how you just typed that in. The answer is no. By default, what R would do is actually form the first, would put what I have highlighted right now as the first column. It would put this as the second column and so on. So that's why I needed to say by row equal true. And then to make this descriptive, I'm going to use an argument called dim names, similar to what we saw with the array function. Dim names equals k dot names, where what I've done is I put in a list what the corresponding rows are, well, wind, distance equal 20, and what the corresponding columns are, beta 0, beta 1, and so on. So that when I run this code and then take a look at it, here we have a nice descriptive way of displaying a matrix so that you can see what's being done. Okay. Then next, just like what we've done before, I use the MC profile package where I use MC profile function where for object I use my model fit from the GLM function. My CM coefficients matrix or contrast matrix is equal to K. Put the results into linear dot combo there. Then I take those results and I use the confident function immediately to find my corresponding confidence intervals, where I say object equal linear dot combo. I want 95% profile likelihood ratio intervals for each distance and I'm not going to make any adjustment for the family-wise confidence level. If I were to then print off the results from this, so again, this would be like the results of confidence intervals for beta 2 plus beta 3 times whatever that distance is. In other words, you can think of it also as the log odds ratio. Here are my results. So for an odds ratio corresponding to a distance of 20 yards, log odds ratio, I get negative 0.6 to positive 2.8. What I could do then is extract out the confidence intervals from the results, apply the exp function there then to find then the odds ratio confidence interval, and that's what you have here. Alternatively, MC Profile has it set up where if you just take the results itself without extracting the confidence intervals first and use the exp function with it, now you have then the confidence intervals that we would want. Nicely labeled. Now note, this is for windy over not windy. We've been looking at the reverse. So how can I do that? Well, one way is just simply now extract the corresponding elements of ci.log.or and invert them and then display them that way. And here's our corresponding confidence intervals. Compare these to what we have for the walled intervals. You're going to see a lot of similarities. You're going to see exactly the same OR hats as well, the estimated odds ratios. Now, do note that there is a little bit of a quicker, easier way to, instead of having to do this manual inversion like this, if I would have started with using CM equal negative K in MC Profile, I would have got this as well. Make sure you understand why that is true on your own. Now, if I wanted to, I could also use the walled function inside of MC Profile and got my walled confidence intervals, and notice how these match with what we had as well. Let's see here. Let's real briefly mention, I don't remember if I mentioned this earlier in my video. Notice how for a distance of 40 yards and higher, we have then the odds ratio confidence interval not containing 1. So there is sufficient evidence to indicate that wind is important when when we have these larger distances. Wind is important relative to the probability of success. Okay, so that gives you some background, some information about how we can include interactions in our logistic regression model, and then how we can interpret the interactions using odds ratios.